The theory of electromagnetism uses a fairly advanced mathematical apparatus, the basic elements of which are vectors and operations on vectors, including operations based on differential and integral calculus. Let us try to take a closer look at these concepts, starting with two fundamental operations, dot and cross product. We will consider vectors in a three-dimensional space, which means that each vector A can be decomposed into three components along arbitrarily selected perpendicular axes x, y, and z. Let A and B be vectors with the components ax, ay, az, and bx, by, bz. These components are just ordinary numbers. The dot product of vectors A and B, also known as scalar or inner product, is defined as the following number. It can be proven that the value of this combination remains the same in any coordinate system, even though the individual components of vectors A and B will vary from system to system. Using this fact, we can now easily show that the dot product of any two vectors will equal the product of their lengths and the cosine of the angle between them. Let us select a coordinate system, such that vector A lies on its x-axis. In that case A has only one, x component, and the dot product of A and B will reduce to the product of their components along the x direction. However, the x component of the vector B is equal to its length, times the cosine of alpha, and thus the result is achieved. From this formula we can also derive an important fact, often used in vectorial calculus: the dot product of two perpendicular vectors is always zero. The cross product of two vectors is a bit more complicated. First of all, the result of it is a vector, not a number. The components of this vector are as follows. As you can see, each component of the cross product is given in the form of some combination of the remaining two components of the multiplied vectors. We can now show that the cross product of two vectors will be a vector perpendicular to each of them, whose length equals the product of the lengths of the multiplied vectors times the sine of the angle between them. As before, we will make use of the fact that the cross product is the same in all coordinate systems. So we can select a system as depicted on the diagram. Since in this system the z components of vectors A and B are 0, their cross product will only have the z component, equal to the product of ax times by. And because the y component of B is given by b times the sine of alpha, the result will be as written. In order to define important differential operators, such as divergence and rotation, we have to introduce vector fields rather than simple individual vectors. A vector field on a space is just an assignment of a vector to every point in this space. Mathematically, it is best to represent such an assignment as consisting of three numerical functions with three real arguments, such that each function assigns to the coordinates x, y, and z the component of a vector in a given direction. Thus, in general, the vector field A is given as follows. Assuming that the three functions ax, ay, and az are smooth, we can introduce the well-known operation of differentiation with respect to the arguments x, y, and z. These operations are called partial derivatives. We may interpret them as representing the rate of change of a particular function when moving in appropriate directions x, y, or z. Let us now introduce the operations of divergence and rotation. The key to these concepts is to treat the differentiation operation with respect to the three coordinates x, y, and z as a vector. This is, of course, a certain abuse of notation, but it turns out to be very convenient. So we will define the following differential vector, called nabla, by giving its components. Consider now what would be for instance the result of a dot product of such a quote-unquote vector, with an ordinary vector. Since the components of the first are not numbers but operators, we have to apply them to the components of the second rather than multiply them. The result is exactly what we call the divergence of the vector field at a point. Similarly, the rotation of a vector field is defined as the cross product of the nabla vector and the vector at a given point. In this way we will obtain two new fields on space, the field of divergence which is a scalar field, and the field of rotation which is vectorial. What is the physical meaning of both operations? Let us start with divergence. Consider an infinitesimal cube with sides dx, dy, and dz. Imagine that the vector field A represents the flow of a certain substance, for example, the velocity field of water in a stream. Let dAx denote the change in the field component Ax with a shift along the x-axis by the value dx. Multiplying this quantity by the area of the side surface of the cube perpendicular to x, we get dAx times dy times dz. It is, as you can guess, a measure of the outflow of a given substance from the cube through the walls perpendicular to x per time unit. For instance, if the component Ax does not change at all, the total outflow will be 0, the same amount flows in as it flows out. If we want to count this amount relative to the unit of volume, we have to divide this quantity by the volume element dx times dy times dz. But in this way, we will get the rate of change of the component Ax along x, dA divided by dx. Analogous reasoning shows that the partial derivatives of Ay over y and Az over z represent the outflows of a given substance along the y and z axes per units of time and volume. Adding up these three numbers, we get the total field outflow per unit volume from the infinitesimal cube. In order to figure out the meaning of rotation, let us consider an infinitesimal square with the sides dx and dy. We will assume that the field has only two components Ax and Ay, and that these components change when moving by the distances dx and dy as depicted on the diagram. Now, we will calculate the quantity known as the circulation of the field along a particular closed curve, in this case the square. The circulation is calculated by following the curve in one direction, for instance counterclockwise, and for every segment multiplying the component of the field parallel to it by the length of the segment. Finally, we add up all these numbers, remembering that when we go in the opposite direction to the field, we have to place the minus sign. The result of this operation is as follows. Once we divide this formula by the area unit dx times dy, we get this, which is none other than the z component of the rotation of the field. Thus the rotation represents the circulation of the field along an infinitesimal curve surrounding a given point. Finally, we can present the fundamental laws of classical electromagnetism, known as Maxwell's equations, in the so-called differential form. These laws connect both the electric field E and the magnetic field B, with electric charge and current, as well as with each other. The first Maxwell equation describes an electric field. It states that the divergence of the electric field E at a point is proportional to the density of electric charge at this point, symbolized by ρ. And since we know that the divergence represents the outflow of a field, the equation tells us that the outflow of an electric field must have its source in the electric charge existing in a certain area. The second equation indicates that the outflow of the magnetic field is constantly equal to 0. This is a direct consequence of the fact that there are no magnetic charges, magnetic monopoles. Magnetic fields are sourceless, so they do not flow out of any point, but only circulate. The third and fourth equations describe mutual relationships between electric and magnetic fields. The third one, also known as the Faraday law, connects the rotation of an electric field with the rate of change of a magnetic field. The usual interpretation is that by changing the intensity of a magnetic field at a given point, we create a rotating electric field at this very point. The fourth equation reverses the situation. Now we equate the rotation of a magnetic field with the sum of two components. The first component represents the electric current density flowing through a given point, while the second described the rate of change of an electric field. Again, the standard reading of this law, known as the Ampere-Maxwell law, is that a rotating magnetic field can be created by either passing an electric current through a point, or by changing an electric field. The lack of symmetry between the third and fourth laws follows from the fact that there are only electric and no magnetic charges.